Okay, we're going to start off with the following differential equation. Y dx add x dy equals 0. Okay, could I solve this by separation? Is this separable?
Yes.
Definitely is. Is this linear? Could you put it in a form that's linear? Yes, you definitely could. Do you notice that on the left side, this is the product xy, the derivative? Is that equal to 0? Now you do. So if we were to integrate, xy equals c is our solution. It's called the general solution. Okay, this is going to be related to the idea of exact equations today. One thing I need us to recall is if we have z that is some function of x and y, then dz was equal to partial f partial x dx add partial f partial y dy. Do you remember what that's called? The dz from last semester? What? The differential. Yeah, this is called the differential. Okay, so what we're going to be looking at is when you set this equal to 0. This part then is called your differential equation. Okay, so all of that leads us to definition of an exact differential. Okay, so a differential expression such as m of xy dx plus n of xy dy is called an exact differential. If it is the total differential of some function f of xy a differential equation of this form that is set equal to 0 is called an exact equation. So in other words, it's an exact equation if the left-hand side is an exact differential. Let's look at the first example. I want to know if the expression 6xy dx add 3x squared dy, I want to know if that expression is exact. Okay, so if we look back up here, for this expression, or this expression really to be exact, this m of xy has to be the partial of some f with respect to x. N of xy has to be the partial of f with respect to y. Can you all think of a function where this would be the partial with respect to x and this would be the partial with respect to y? 3x squared y. So if we take our f of xy, or our z, to be 3x squared y, the dz then, our total differential, partial with respect to x, so in this case 6xy dx, partial with respect to y is 3x squared dy, which is in fact partial of f with respect to x dx, and then the partial of f with respect to y dy. So, yes, that expression is exact. Now, that one we were able to do in our heads. Things are going to get a little tougher if I give you some more complicated expressions. So there is an easier way to determine if the expression is exact. So we're going to talk about how else can you tell besides finding this function, and then we'll talk about how does that relate to solving. So here's our theorem. Let m of xy and n of xy be continuous and have continuous first order partials in a region R. R is defined by x being between A and B, and then y being between C and D. Then m of xy dx, add n of xy dy equals 0 is exact if and only if the following is true. The partial of m with respect to y is equal to the partial of n with respect to x. That should make sense up here. This is your m of xy. If you take the partial with respect to y, you get 6x. Up here, take the partial with respect to x, you get 6x again. So take those two partials, they're equal, you can tell that that's exact. Few questions for you. This should remind you of something from last semester. It helped you figure out something about a vector field if the vector field was conservative. Helped you determine if a vector field was conservative. After you figured out that the vector field was conservative, what did you normally do? What did you have to find? The potential function. Yeah. Solving an exact equation is very similar to finding a potential function. So finding a solution is going to be like finding a potential function. Do you know what the if and only if means?
It's not this, then it can't be.
Right. This condition is sufficient and it's necessary. So if this is not true, then there is no way that your equation is exact. Okay. So let's do a few examples. First one, 9x squared y dx. Add the quantity 3x cubed plus 1 dy is equal to 0. Okay, I told you on your test and on your final, you will have to be able to determine when to use each method. So my first question to us, is this equation separable? Could we get all the x's on one side, all the y's on the other? Yeah, definitely is. So we could solve this by separation. Is this linear? Or could we put it in a form that's linear? Is the derivative to the first power, is y to the first power, are all the coefficients in terms of x? Yeah, so this is linear. Okay. So new today, we need to know, is this exact? We're going to find the partial of m with respect to y. So whichever one has dx, take the derivative with respect to y, we get 9x squared. Then we're going to take the partial of n with respect to x. So dy, take the derivative with respect to x, we get 9x squared. These are equal, so yes, our equation is exact. So really, we have 3 different solving options. We're going to do the exact one. Okay, here's the deal when you have an exact equation. Your solution is going to be of the form f of xy is equal to c. F of xy is basically the potential function. So we know that f of xy is going to be the integral of partial of f with respect to x dx. You can choose x first or y, it doesn't matter, like the potential function, I just chose x. That's going to be this one. So we're going to integrate that 9x squared y with respect to x. We get 3x cubed y, and then if you remember, your constant could be a function of y. When we did potential functions, we used k of y. I don't know why this book uses g, so I'm going to use g. After this then, partial of f with respect to y, that has to be equal to 3x cubed plus 1. So we get that 3x cubed plus 1 is equal to, take the derivative with respect to y, we get 3x cubed plus g prime of y. So we get 1 equals g prime of y. Our g of y then is equal to y plus c. Our solution then, our f of xy is 3x cubed y plus c. So we get 3x cubed y plus y. The c is always put on the right side. So that is our solution. Right now this is defined implicitly. Could we find an explicit solution here? Yeah, factor out the y. For some reason with exact equations, normally that's not done. Normally it's just left in this form. I'm not sure what your homework is going to ask for, so just pay attention if your homework asks for implicit or explicit. Okay, do we get the gist of this? It's a potential function. It's really nothing new. Okay, this does lead to a few other things though. Yesterday we talked about the integrating factor. So that was the mu of xy when we were solving linear equations. Here's the idea here with exact equations. Sometimes it's possible to turn an ordinary differential equation into an exact equation by multiplying by some integrating factor using the same notation as yesterday, mu of xy, so that when we do that, we'll get mu of xy times m of xy dx plus mu of xy n of xy dy equals 0 is exact. So sometimes we multiply by an integrating factor and we can turn an ordinary differential equation into one that's exact. This is not the case most of the time. It happens occasionally. I will not be asking you to find the integrating factor. I will ask you, is this an integrating factor? Or I'll give you one and say, use this, now solve the equation. So that's what we're going to do now. Okay, our equation is negative y squared dx. Add x squared, add xy dy is equal to 0. First question, is this separable? No, what is the issue? The x squared plus xy. Okay, next one. Is this linear? No, definitely not. Why not? Y squared. Is this exact? Bless you. So we would take the partial of m with respect to y, which in this case is negative 2y. Take the partial of n with respect to x. Take the derivative with respect to x. We get 2x add y. So this is not exact. So far, we don't have a way to solve this. Now, I will tell us that we can use mu of xy is equal to 1 over x squared y. So that's going to be our integrating factor. What we're going to do, we're going to multiply by that integrating factor. We're going to prove that this equation is exact, and then we're going to solve it. So we're going to multiply that entire equation by 1 over x squared y. When we do that, we get negative y over x squared dx plus 1 over y plus 1 over x dy is equal to 0. Now partial of m with respect to y is negative 1 over x squared. Partial of n with respect to x is negative 1 over x squared again. So now this is exact. Okay. So finding our solution then. I'm going to start by integrating with respect to x first. So negative y over x squared dx. When you do that, you get y over x plus g of y. Now we need to handle that y. We want our partial of f with respect to y to be equal to 1 over y plus 1 over x. From above, if I take the derivative with respect to y, I get 1 over x plus g prime of y. My g prime of y then is equal to 1 over y. If I integrate that, I get my g of y to be the natural log of y. So my final solution then, going back here, is y over x plus the natural log of y is equal to c. Can I find an explicit solution here? Nope. Okay. We are going to do one more. And by one more, I mean you're going to do one more. Does that work? Okay, great. Yes.
Will it tell us to use the mu? It'll give
Yes.
us that?
Yes. Either it'll give it to you, or it'll give you that and ask you, is this an integrating factor? And you would say, yes, it works, or no, it doesn't. But you do not have to find it on your own. Okay, here's the one that I would like you all to do. Good luck. get a solution before you find C, can you check with the person next to you, please? Can you check in with the person next to you, wherever you are?
What you doing for your? Because I just moved in around. But then when I get one in here, when you try to find the solution.
Oh, I didn't, okay, I messed up something. Yeah.
I think you're supposed to do the one with the top.
You guys do.
How are we doing? When you're ready, here's the solution I got.
Oh, there's initial expression. Oh, I forgot to do that.
Sure.
What do we sure? So we got?
I mean, it's some, multiply by in a different form, but yeah.
I was so.
That's not the factor, honestly. Yeah, exactly. Not the y multiplied by 2.
Yeah, I went for
You
Y.
have the-
I do. Okay. Are we ready to start looking at work?
Yeah.
Okay. Do we want to talk through it, or do you just want to see my page's solution?
See it.
Just see my work? Okay. There's kind of the bulk of it. Can you see that? Probably not that well. This is the equation you should have gotten to check when it's exact. What tripped us up? It seemed like it was this, integrating cosine x sine x. You guys could do all that stuff, but when you got to here, you got stuck?
Did you just do, for the second time you do the partial, did you just do plus g prime of x no matter what the other term?
No matter what this one is? What do you mean?
I don't know. G prime of x.
You take the derivative of this with respect to x.
Oh, okay.
Because that's what you haven't done yet. Okay. Did we get the general idea? Just maybe got stuck in somewhere? Like, did we put it in the right form? Did we verify the equation was exact? Yes? Great. How do we feel about exact equations?
Good.
Yeah, they're not horrible.